previous videos, we looked at the different failure modes under static loading for a mechanical fasten joint: net section tension, bearing, shear tear out, fastener shear, and fastener pull out. In this video, we are going to develop simple analytical models for predicting the onset of these failure modes. Now, before we do that, we need to cover a few basic assumptions for our predictions. And the first very critical assumption is that we will only consider the failure of ductile materials, both in the fastener as well as the sheets. Now, the reason for this can be illustrated with this picture of a sheet with a fastener hole in it under a tensile load. And on the right, we will consider what would happen in a brittle material, and on the left, we will consider what would happen in a ductile material. In a brittle material, well, actually in both materials, as we apply a load, as we've seen earlier, there will be a stress concentration associated with that fastener hole. Now, if we continue to increase the load, the stress at the edge of the hole will increase because of that stress concentration. And if that material is brittle, that will continue until the stress at that stress concentration reaches the ultimate strength of the material, and then we will have failure propagate along the plate. In a ductile material, things are a little bit different. It will not suddenly fail like this. Rather, as we increase the load, the material will start to yield or plastically deform, which will cause a redistribution of stress along the width of the plate. And in fact, it's a very easy and simple approximation that at final failure, you will have a uniform stress along the width of the plate equal to the ultimate strength of the material. This is convenient for developing our models for failure because we can ignore the stress concentration of the hole and just utilize the fact that plasticity will redistribute loads and result in a uniform, approximately uniform stress equal to the ultimate strength at final failure. Related to this plasticity assumption is that all fasteners carry the same load at static failure. So here we have 12 rivets connecting these two plates, and below static failure you will actually have a different amount of load transfer by each row. But just like plasticity redistributes the stress along the width of the plate, the highly loaded rows will start to plastically deform, which will redistribute load to the lower loaded rows. So at final failure, we can assume that the total load is distributed amongst all of the fasteners that transfer load from one plate to another. Now, that load transferred from one plate to another is a very important thing to keep in mind, and that's related to the load path. So if we consider these two joints here, one with 2 rows of bolts and this one has 4 rows of bolts, you have to be mindful of how many rows actually transmit the load. So in this upper case, the load is transferred from one plate to another by 2 rows. In the lower case, you actually have 2 rows transferring it from the upper to the lower plate, and then 2 rows transferring it back from the lower plate to the next upper plate. So in both of these cases, the load F is transmitted from one plate to another by only 2 rows of bolts. So you would look at the failure in relation to those 2 rows of bolts. Okay, so now let's jump into developing our simplified models for failure modes. We will start with net section tension failure, which we saw as a failure that will occur when the stress in the net section, so that is the smallest cross section of the plate, reaches the ultimate strength of the sheet material. Okay, so we're using that plasticity assumption. The stress is uniform and equal to the ultimate strength. So we can define that force as the net section area times the tensile ultimate strength of the material. If we look at this net section cross-section, which is this hatched area, we would have this width minus the bolt, the regions where the bolt are. It basically cuts out area. So we would get width minus the number of fasteners times the diameter of the fastener, and then multiplied by the thickness. That will define our net section area, and we multiply that by the ultimate tensile strength of the material to get our net section tension failure for the plate. Next, if we look at bearing failure, this failure will occur when the stresses acting on the projected area of the sheet on the bolt exceeds the bearing stress allowable for the sheet material. So this is a material property. So the bearing failure force is our bearing area times that bearing stress allowable. Now, to define the bearing area, we need to look at that projected area, and when there's multiple plates, you can have more than one bearing area. So here we have the upper sheet is resisting in one direction, the lower sheet in the other direction, so we have a purple and green area. Now, if both of the sheets are the same thickness and same material, all of this will come out the same, but you can join dissimilar materials or different thickness materials, so you can get a difference in the bearing failure force for those different plates. In this simple case, our bearing area is the diameter times the thickness, and then we would multiply that by our bearing strength of the sheet material. Now, it's important to realize that this equation gives you the force acting on the sheet by the bolt at failure, and not the applied force to the entire joint. It's only looking at a single bolt. So you will have to then look at the load path and figure out how many bolts transmit the load from one plate to another, and multiply by this force by that appropriate number to get the failure force for the entire joint. And we'll look at this a little bit later when we do an example problem. Next, we have shear tear-out failure, which is a failure that will occur when the shear stresses acting on the area between the bolt and the joint edge exceeds the shear strength of the sheet material. So the shear tear-out force is the area for shear tear-out times the shear ultimate strength of the material. If we look at the image of the bolt, our shear tear-out area is defined by this crosshatch area and the same area on the other side, because we have two areas resisting that failure mode. So that gives us 2 times the edge distance B times the thickness T. And again, this equation gives you the force acting on the sheet by the bolt at failure and not the force applied to the entire joint. Next, we have bolt shear failure, which will occur when the shear stress acting in the area of the bolt exceeds the shear strength of the bolt material. So our bolt shear failure force is the area resisting that shear times the shear strength of the bolt, okay, not the plate. This is a failure mode of the bolt material. And so that will be the cross-sectional area of a bolt, which is pi over 4d squared times the shear strength of the bolt. And this n refers to how many planes actually resist the load transfer. So I can illustrate with that with this subfigure, where if we have 2 plates joined, there's 1 plane resisting the load transfer. So n would be equal to 1. If we have 3 plates, we have 2 planes of shear resisting, and when we have 4 plates, we actually have 3 planes of shear resisting the load transfer. So you have to be mindful of how many planes within the bolt resist the shear force. And again, this equation is for a single fastener, so you have to look at how many fasteners actually transmit the load when looking at the failure force for an entire joint. The final failure mode is fastener pull-out failure. However, this failure mode is much more complex. It's a little bit more difficult to develop an analytical model because it's highly dependent on the bolt head geometry. So you can imagine the shape of the bolt head will have a huge influence on whether or not it gets pulled through the sheet. So it's a little bit beyond what we will cover within this course. So just be aware that it would be something that you would typically look at in terms of test data, and you may have to do things like adding washers or using a different fastener head to prevent this failure mode if it was at risk of occurring.